Okay, this will be at least part one of this PyMEG GUI interface screencast. So to get started, let's move into the directory that we have downloaded and installed PyMEG, or at least downloaded. There's really no install at the moment. My path is as such, and I'm going to cd into the GUI GTK directory. This is where all the graphical code is. Currently it's written in GTK using Glade. And to launch, we're just going to type pymeg.py. This will launch the main window. Here I have a sort of a debugging test file already loaded. Let's delete that and start from scratch. Loading in a raw, looks like pre-processed, offset corrected, decimated MEG file. We're going to only load the MEG channels, excluding reference, trigger, and external channels. And we're going to load in every point. Had this been an epic file, we would have had the ability to select which epics we wanted to load. The file is now loaded. At the top level, we can see the data file's name and path. Double-clicking will allow us to see objects underneath, and we can keep delving deeper if we wish. So, going back up, we will load in another file. This is let's pre-process this file. So we have a raw data file. Open up the function menu, and we can see for every object we select what functions are available to us. So configuration file, can't really do anything with, but we can view some of the system configuration settings. The header, head shape file, and the actual data. So let's take a quick look at the data with a basic data editor written in using PyLab or Matplotlib. Right now it's sort of truncating the view to about 3 seconds. We see one bad channel here. Going into the preferences tool, we can reduce the number of channels and increase the spacing. We can go through the data if we wish in time, watching this axis below. It's being updated as we step through. We can step up in channels, see different channels, as well as taking a quick look at the power spectrum. So for example, channel 88, you can see it's a power distribution with a spectrogram and current source density. Selecting a different channel will update that, replacing the spectrogram but adding an additional line for the current source density. What else do we have available here? We know from previous knowledge, I know that channel 248 is the bad one. We can select all channels but that one. Now it's excluded from the view. What else do we have available? Let's zoom in a little bit, go back, and we can make a selection. This looks like a blink here. We can make a selection over that and plot the contour display. Looks like we have a DC offset, so let's go ahead and DC offset with this selection. taking so long? It's a pretty big file. Also, I'm doing a screencast, which is taking about half of my CPU power, so everything will be a little slower in the screencast than in real life. I know it's taking so long. Now it looks like it finally finished. DC offset correction. We want to plot this this selection here, so instead of making another selection, I'll select that time selection from here and update the contour display. Doesn't look particularly eye-ish. Doesn't look like an eye blink to me. Select another window. This is between 2 and 2.5 seconds. We'll update the window. Nothing particular eye blinky to this either. It could be EKG. So what else? Let's close the data editor. We have available to us a 3D plotting tool, and it's just a proof of concept here. Definitely could be a lot fancier. Put a lot more time into it. What we're going to do is plot the head shape points with the channels, the channel locations, as well as the fiducial, the digitized fiducial points. So we're going to select the object we wish to add to the plot. We're going to add the head shape points as well as RPA, LPA, and Bayesian. We're going to go up a level, go into the data, find the channels, and here we're going to grab we have an upper and lower channel position, so we're going to grab this is the upper position. We're going to grab the lower position and add that as well. I'm going to select all the objects, all the variables we wish to plot, change the colors. That should be suitable. So now we have a let's change the fiducial sizes to something a little bit more apparent. There we go. We got a 3D plot of the head shape and the channels and the fiducials. What else do we have available to us? So like I said before, only functions that are applicable to that object will be available upon clicking that variable. So for data, we can do a time frequency transform, power spectral density. We can calculate some grid points for source space, localization, projection, etc. A couple of pre-processing functions. Let's actually create an average of this long data set using, this was an auditory evoked, actually this is a motor task. So we're going to actually see what kind of event-related potentials came from. Actually, no. I'm going to go to another file, an auditory evoked response data set. This was a left ear stimulated auditory experiment. So the subject got a left ear stimulus tone every 1.5 seconds. And we want to epoch this data set. From previous knowledge, I know this is the event value, 4238. We have some Boolean logic available to us. We can specify a time range with multiple events. So, for example, if they had responses in this experiment, they were required to respond within such and such period of time, we could limit looking at events that had responses within some specific window, but that's not the case for this experiment. So we're going to specify a time range, pre and post event, to cut this data file up and average it. So I'm only going to be interested in looking at half a second post stimulus. We're going to test the logic here. 200, since I didn't actually specify any other events for the logic operation, we're going to get the same number that were in there. So 200 events pass this logic, and we're going to now average this. We have a new object in our window called epoch data. Let's rename that so it's not confusing if we decide to re-epoch. And let's plot this. So this is our evoked response to an auditory stimulus. I'm going to go ahead and offset correct that and look at the contour display, the topographical map of the fields of the M100. So this is let's go back to that. This is a auditory evoked response, is both contralateral and ipsilateral. If we wish to look, let's look at the channel labels, replot, so we can find a channel that's over some of the field that has some maximal power. So for example, 174 has a lot of power underneath it. Go back to the data and look at the power spectral density of 174. We should see a little peak in the line at 40 Hertz. So take a look at the time frequency transform of 174. Now we have a new object called TFT, and we can plot that. Look at the evoked power. See, seem to have stole my previous window. So not much evoked power at 40 Hertz. We have plenty at at 75, which is interesting. Let's look at the intertrial coherence, and we see plenty of phase locking factor or intertrial coherence at 40 Hertz. I think that'll pretty much do it for this screencast. Again, PyMEG is very beta. It's just a proof of concept. Some tools you have available in Python. All of this is free, open source, using Python, GTK for the GUI, NumPy and SciPy for the numerical libraries for a lot of the processing, VTK, also open source for doing some of the 3D plotting. Thank you, and if you wish to download, check the website that you're viewing this screencast, and check out my page at GitHub. Just go to GitHub and search for PyMEG, and you should see the project. My name is Dan Collins, and feel free to email me if you have any questions, dan.collins@ucdenver.edu. Thank you.